Hi everyone, I'm Apaar, Technical Marketing Engineer for the Cisco Secure Firewall. In this video, we will talk about Dynamic Virtual Tunnel Interface, or DVTI in short, which was introduced in the Threat Defense 7.3 release. Before we talk about DVTI, let's take a quick look at static VTIs. In Threat Defense Release 6.7, we had introduced SVTI, using which we could encrypt the traffic based on routes instead of access lists. This helps simplify the VPN configuration by not requiring to manage complex access lists and ordering them correctly in the crypto maps. All the traffic that hits the VPN tunnel based on the routes will get encrypted and sent to the peer. In Release 7.3, we have added the support for DVTI, which allows for dynamic instantiation and management of VPN tunnels. DVTI uses IP unnumbered functionality to borrow the IP address from a loopback interface, which helps observe the IP addresses. Now we don't need a separate IP address per spoke. Just one IP address would be sufficient to build the tunnel with all the spokes. We can also use any of the routing protocols like PGP, EIGRP, or OSPF to exchange the routes over the VPN tunnel. Now let's take a look at how DVTIs work. When a spoke tries to build a VPN tunnel with a hub, the DVTI configuration is cloned and a new virtual access interface is created. This interface is created dynamically and remains active until the VPN tunnel is active. All the traffic that hits this virtual access interface is then encrypted and sent to that particular spoke. If we look at the differences between SVTI and DVTI, we see that there are multiple advantages with DVTI in case of big VPN setup with multiple spokes. First, SVTIs are point-to-point, whereas DVTIs are point-to-multiple. This means that on the hub we need one SVTI per spoke, whereas we need only one DVTI for the entire VPN topology, which can support hundreds of spokes. This is because the DVTI configuration is cloned into a new virtual access interface whenever a new spoke tries to connect. This eases the administration tasks and reduces the complexity of managing hundreds of VPN tunnels even further. Whenever we add a new spoke, we only need to configure the tunnel on the spoke without requiring any VPN configuration related changes on the hub. However, your routing and NAT configuration may require some changes depending upon the setup. Last, if a spoke is using a DHCP address and the address changes, then in case of SVTI, we would need to update the IP address on the hub. However, with DVTIs, there are no changes required on the hub. The spoke will initiate the tunnel using the new IP address and the old VPN tunnel will be deleted. Now let's take a look at it. Here's the topology. We have the hub FTD and two spokes, spoke 1 and spoke 2 at the remote branches. The hub will be configured with DVTI and the spokes will connect to this DVTI to bring up the VPN tunnels. Let's jump to the FMC and see how we can configure DVTIs to build hub and spoke type VPN topologies. First, we'll go to the hub, click on Add Interfaces, and then add a new loopback interface. For a more detailed explanation on loopback interfaces, please check our YouTube channel for a dedicated video on loopback interface. After configuring a loopback interface, we will go to Add Interfaces and add a virtual tunnel interface. Since this is the hub, we will select the tunnel type as dynamic. We will provide a name for reference, a security zone, and a template ID. The tunnel source will be the outside interface, and in the next dropdown, we will select the IP address. As we see, the option to configure an IP address is grayed out. For DVTIs, we can only borrow an IP address from another interface. In our case, we will select the loopback interface we had created earlier. Then click on OK to add the DVTI and then save the changes. Then we'll go back to device management and this time edit the settings of spoke 1. We'll click on Add Interfaces and add a new virtual tunnel interface. For the spoke, the tunnel type will be static, as the spoke will initiate the tunnel and have a static connection to the hub. Similar to the DVTI, we will provide a name for the interface, a security zone, a tunnel ID, and select the tunnel source. We'll also provide an IP address for the interface, then click on OK to save the tunnel, and then save the changes. Then we'll go to spoke 2 and add a virtual tunnel interface in the same way. Now we'll go to Devices, VPN site-to-site, and add a new site-to-site VPN topology. We can give any name for reference and then select route-based VTI. Since this is a hub and spoke type topology, we'll select hub and spoke. For the hub node, we will select hub as the device and the DVTI we had configured. In the advanced settings, we will enable the option Send Virtual Tunnel Interface IP to the peers. This option allows the FTD to send its interface IP address to the remote peer, so that the peer can install a /32 route in its routing table. This option is needed if you are using static routes or BGP. Without this route, the peer will not know how to reach this device and may end up routing the packets through another interface. Click on OK to add the endpoint. Then we'll add a spoke node. We will select spoke 1 and the VTI that we had created on spoke 1. The advanced setting, Send Virtual Tunnel Interface IP to the peers, is selected by default for the spokes. Click on OK to add the endpoint. We will also add spoke 2 as a spoke node in the same way. Click on Save to save the topology. Next, we will configure the routing protocol. In this demonstration, we will use BGP. We'll go back to Device Management and select the hub node. Then, we'll go to the Routing tab and go to BGP towards the bottom left. We will enable BGP and provide a AS number, and then save the changes. Then, we'll go to BGP IPv4 and click on Enable IPv4 to enable BGP version 4 on the FTD. Now, we'll go to the Neighbor tab and add spoke 1's tunnel interface IP as a peer. Provide its AS number and then enable the address. Then click on OK to save the peer settings. We'll add spoke 2 in the same way and provide its details. Other neighbor settings may be modified as per the requirement or can be left at default. In this demonstration, we'll leave them at default. Click on OK to save the peer settings. Now we'll go to the Network tab and add the network behind the hub, that's 10.254.254.0/24 as a network to be advertised into BGP. Click on OK and then click on Save to save the changes. Now we'll go back to Device Management and this time edit the settings of spoke 1. We'll go to the Routing tab and configure the BGP settings in the same way as we did on the hub. On the spoke, we'll add the hub's tunnel interface IP address as a peer, provide its AS and enable the peer. Click on OK to save the peer settings. Now we'll go to the Network tab and on spoke 1, we will advertise the network 10.110/24 into BGP. Then click on Save to save the changes. Now we'll go back to Device Management, then go to spoke 2 and repeat the same steps to enable BGP, add hub as a peer and advertise the network 10.2.2.0/24 into BGP. Then click on Save to save the changes. Now that we have configured the interfaces, VPN topology, and the routing protocol on all the devices, we will go ahead and deploy the changes. Now let's jump to the CLI of the devices to look at some outputs. On the left we have the hub and on the right are the two spokes. First, let's check the interface configuration. As we see, the IP address of the loopback interface, the DVTI, and the virtual access interface is the same. This is because the DVTI is borrowing the IP address of the loopback interface. And once the VPN tunnels are established, its configuration is cloned into a virtual access interface, and so the virtual access interfaces also use the same IP address. If we check the settings of the tunnel interface, we see that it is using loopback 1 as IP unnumbered. If we do a show crypto IQ to SA, we can see both the tunnels are up, and we see that the local IP address is 100.1.1.1 and the remote peers are 1.1.1.1 and 2.2.2.1, which are the outside IP addresses of spoke 1 and spoke 2 respectively. Next, let's look at the output of show crypto IPsec SA. we can already see some endcaps and decaps for both the peers. These would be the packets exchanged to bring up the BGP neighborship between the hub and the spokes. Now we'll ping the tunnel interface IP address of both the spokes, and we see that the pings are successful. From the output of the show BGP command, we can see the hub is learning the remote networks behind both the spokes. And from the output of show route command, we can see both the routes are correctly installed in the routing table. Another thing we notice in this output is that the hub has added 2/32 routes for the spokes tunnel interface IP addresses through their respective virtual access interfaces. This is because of the checkbox send virtual tunnel interface IP to the peers we had enabled on the spokes as part of the VPN topology configuration. If we go to spoke 1 and do a show route, we can see a route for the hub's inside network, as well as a /32 route for the hub's tunnel interface IP address through the VTI. And if we check on spoke 2, we'll see the same routes there as well. If we ping the tunnel interface IP address of the hub from the spokes, we see that the pings are successful. We can also see the current status of the tunnels from the FMC. If we go to Devices, Site-to-Site VPN, we can see the status of the topology. If we hover the mouse over the tunnel status, we see that both the tunnels are active. If we click on the drop-down next to the topology name, we can see the status of each tunnel in a lot more detail. As we see, both the tunnels are in active status. As we saw in this demonstration, we were able to add a hub and spoke topology within minutes. If we need to add more spokes, all we have to do is configure a new VTI on the spoke and add that spoke to the VPN topology, without having to make any VPN related changes on the hub. However, please note that we may have to make some changes to our routing protocol and NAT configuration depending upon the setup. This concludes our demonstration for the dynamic virtual tunnel interface. Thank you very much for watching the video. I hope you enjoyed it. See you next time.